Let us next see number 8. Here we are given the function f from this ray, the set of all non-negative real numbers 0, infinity, into this other ray, the set of all real numbers greater than or equal to 4, or you can also call it an interval 4, infinity. And the rule that defines f is this: f of x is x squared plus 4. We have to show that f is invertible with the following inverse. The inverse function, of course, would map 4, infinity into 0, infinity, and this is what we have to show, that this function, whose value at y is square root of y minus 4 and which has domain 4, infinity and codomain 0, infinity, is the inverse of f. That's what we have to show. We start the solution like this. We are first of all going to show that this function is a legitimate function, that is, it's well defined. But I forgot to write something. I wanted to give a new name to this function. We cannot just simply call it f inverse before showing that it is really the inverse of f. So I wanted to give it some other name, say g. So you should start in the solution not exactly like this, but you should first write the line, let g be this function. Okay, you write like this: let g from 4, infinity into 0, infinity be the function given by g of y equal to square root of y minus 4. Alright. And now let us show that g is well defined. So what you do for that, you take any point in the domain of g, 4, infinity. What does that mean? It means that y is a real number which is greater than or equal to 4, and that is why y minus 4 is greater than or equal to 0. Y minus 4 is a non-negative real number, and you know that non-negative real numbers have non-negative square roots which are also non-negative real numbers, and that is why not only is this square root a real number, it is itself greater than or equal to 0, or in other words, it belongs to this interval. So for any point in the domain, the function g maps that onto a point in the codomain, a unique point in the codomain, and that is why g is well defined. Now that we have shown that g is well defined, that g is a legitimate function, we can next go for showing that g is really the inverse of that f. For that next part, we take any element x in the domain of f, that is 0, infinity, and then we calculate g composition f of x, because this composite map will have the same domain as f has. So that is why it makes sense to evaluate g composite f at x, which by definition is g of f of x. Now what is f of x? You go back to the question, f of x is x squared plus 4. And what does g do? G does this: square root of the input minus 4. That means square root of x squared. And here, let me remind you of something. This is in general equal to the modulus of x, the absolute value of x. Actually, this is equal to this, not just simply x. Okay, do not make the mistake of simply just cancelling square and square root. I mean, of course, you are doing just that, but the result is not simply x. In general, it's mod x. But your x is coming from here. That means x is a non-negative real number. It is greater than or equal to 0, and that is why this is equal to x. So you see that g composite f is the identity function of this interval. There is, of course, one more thing to show. And that other thing is this: for any y in this interval 4, infinity, we next calculate f composite g of y. Just like 0, infinity was the domain and codomain both for the composite function g composite f, This one is both the domain and codomain for this other composite function. So this by definition is f of g of y, and g of y is square root of y minus 4, and f of that is its square plus 4. This time, however, when you cancel square and square root, you straight away write y minus 4, and we are no longer writing modulus y. The reason is that we already know that y minus 4 is non-negative, it's greater than or equal to 0. Had it been negative, this square root would not have been a real number at all. It would have been a non-real complex number. And how do we know that y minus 4 is actually greater than or equal to 0? That is because y is coming from here. Y is greater than or equal to 4, so y minus 4 is non-negative. So cancelling square and square root, you simply get y minus 4. Then after cancelling minus 4 and plus 4, you get y. So just like that one is the identity function on 0, infinity, this one is the identity function on 4, infinity. And that is why, by definition of inverse functions, we can now say that because of these two things, f is invertible and its inverse is that function g. You write this last line yourself, and there the solution ends. Number 9 is also similar. This time we are considering another such function f from 0, infinity into minus 5, infinity. Same type of rays or intervals. Closed on the left side and open on the right side. And the function f is given by this formula. F of x is 9x squared plus 6x minus 5. Again, we have to show that f is invertible with the inverse given by this expression. You already understand that the inverse will be a function from this into this, so I did not write that. Okay. Instead, this is the proposed inverse, which at the point y has the value square root of y plus 6 minus 1 divided by 3. And the solution will be similar, so let's do it. So this time I start the solution more properly by actually naming the function. Define g from minus 5, infinity into 0, infinity by that given formula. G of y equals square root of y plus 6 minus 1 divided by 3. Now the first job is to show that this g is well defined, that it's a legitimate function. So we take any point y in the proposed domain minus 5, infinity. This means that y is greater than or equal to minus 5. And then we add 6 to both sides. Why? Because we want to know about y plus 6, that is why. So adding 6 to this side, you get 1. Alright. Now y plus 6 and 1 are both positive real numbers. You know that y plus 6 is positive because it's greater than or equal to 1, and 1 of course is already positive. So you can take square root on both sides of this inequality without any problem, and the inequality will maintain its direction. It is strictly greater, not strictly greater, it's still greater than or equal to 1. This square root. Actually you also have square root here, but square root of 1 is just 1. Okay. So what do you have? Square root of y plus 6 is greater than or equal to 1. So this minus 1 is greater than or equal to 0. That divided by 3 is also greater than or equal to 0, because 3 is positive. In other words, this entire thing, this ratio is a non-negative real number, greater than or equal to 0, and that's why it belongs to this. So this tells us that yes, g is a well-defined function. Now we can go for showing those two things to prove that g is actually the inverse of our f. So we next, as usual, take x in 0, infinity, the domain of the original function f. And then because the function f itself is somewhat complicated, more complicated than the previous one, so we decide to not go for the entire solution at one go. Instead, let us first manipulate f of x itself. This is our f of x, 9x square plus 6x minus 5. So what we do, because square root is there in the formula for g, so we think that maybe we will get some advantage if we bring in a square, and it turns out that that actually gives us an advantage. So you already know what we are doing here. We are completing the square by gathering those terms that would give us a perfect square and then adjusting for the rest. Already we have 9x square here, so this is the square of 3x plus 2 times 3x times 1 plus 1 square. This 1 square is extra, so now minus 5 will become minus 6, and this part becomes the square of 3x plus 1. So f of x equals 3x plus 1 whole squared minus 6, and that implies f of x plus 6 equal to the square of 3x plus 1. And now we go for the actual calculation. G composite f of x, which is g of f of x. By the definition of g, this is equal to square root of f of x plus 6 minus 1 divided by 3. And now you are having the advantage because this itself is a square. Alright, so after cancelling square root and square, ideally you should put absolute value of 3x plus 1, not just 3x plus 1. Not immediately, but actually that will be equal to 3x plus 1. How do we know that? Is 3x plus 1 greater than or equal to 0? Yes. X itself is greater than or equal to 0, so obviously 3x plus 1 is greater than or equal to 0. Not just that, actually it is greater than or equal to 1. So the absolute value reduces to ordinary 3x plus 1. Then after cancelling 1 and minus 1, and then in the next line after cancelling 3 and 3, you get x. So this part is okay. You notice one more thing, that you may get hopelessly lost in simplifying this expression if you just simply put this here. Okay, I mean you won't get it immediately, but this helps. So next we take any y in minus 5 comma infinity, and this time we go straight for f composite g of y, which by definition is f of g of y, and by the definition of f, this is 9 times the square of g of y plus 6 times g of y minus 5, which from the previous calculation you already know is this, the square of 3 times g of y plus 1 minus 6. Minus 6 is outside. Now we stop the calculation here. If you want, you can continue. Okay, I have for some reason decided to see what this becomes ultimately separately. So here I apply the definition of g. By definition, g of y is this, square root of y plus 6 minus 1 divided by 3. And you can now clearly see that in 2 steps from here you are going to get this. First you cancel 3, that is one step, and then in the next step you cancel minus 1 and plus 1. And then you cancel square root and square and get y plus 6. Y plus 6 is already positive, so here there is no problem writing simply y plus 6. Why is y plus 6 positive? That is because y is coming from here, and which means what? That y is greater than or equal to minus 5, so y plus 5 is non-negative. Add 1 to that and you get positive y plus 6. So now you can resume your calculation. Because of this fact, f composite g of y, which is this, now becomes y plus 6 minus 6. So that way you are getting y. And that is why, because of this one and the previous calculation, f is invertible and its inverse is the function g. Please write this last line and complete the solution.